Okay, picking up exactly where we left off, we said our plan of attack here, to find this exact area, we're going to fill this area up with infinitely many rectangles, and when I fill it up with infinitely many rectangles, so those rectangles keep getting thinner and thinner and thinner and thinner until they become line segments, and then I add up the lengths of every single line segment, infinitely many line segments, you get area. And if you have a really good imagination, you can kind of imagine that each one of these things getting smaller and smaller and smaller till it's all line segments, and then this whole area would just be colored in. It'd be solid with each and every line segment. Okay, so let's get to it. Area equals n goes to infinity, the area of each one of those rectangles. Here's why we did summation notation. This is cumbersome to write out. Area of S1 plus area of S2 plus area of S3. That's cumbersome. So I can use summation notation for that. So that's the limit as n goes to infinity. I'm going to zoom in a little bit. Yeah, let's make that focus. That's the area, that's the limit as n goes to infinity of k equal 1 to n, area of S sub k. And then we can go that we know, we don't need to be in that much. Then we know that the way we find the height of a rectangle is height times width. So going on to the next page. Okay, recall from section 5.1, we used equal width rectangles and we let the width of the rectangles be represented by delta x. In this problem, we are also using equal width rectangles, so we will let the width of each rectangle again be represented by delta x. So just repeating what we had on the previous page, that we're adding up, we're taking the limit as n goes to infinity of all those areas, introduce summation notation because that's cumbersome. Then we know that area is height times width. This was all on the previous page. But now the width is just delta x. Now we need to find each one of those things, the height and delta x. So delta x is easy. That's down below here. Recall, we are considering f of x equal x squared minus 16 between x equal 1 to 3. And it is still true. Zoom in just a little bit here. See these things down at the bottom better. And I do apologize. I know it's close to the end of Calculus 1 and you've watched all these other videos. I apologize if some of the videos are not of the best quality. I was a newbie in doing videos. We did these all because of the pandemic. I much prefer teaching in person. But we did learn before in the previous section that delta x was given by b minus a over n. So for this problem, delta x is going to be 3 minus 1 over n, or 2 over n. And so since n is not a concrete number, we're letting n go to infinity, that's the best we can do. And then just like before, and we have this point right here, that is the height, that y coordinate is the height of, in this case, rectangle S sub k, that y coordinate each time is the height. And so that's what we have here. The height of S sub k is f of x sub k. And that S sub k is just our generic rectangle that kind of represents any rectangle. So moving on to the next page. So we now know that delta x is 2 over n, and the height S sub k is f of x sub k. And I just repeat everything I already had. I don't know why I repeat everything I already had, but it may be for emphasis that all we are really doing here is adding up areas of rectangles. That's all we're really doing when we're adding up areas of rectangles. It just happens to be infinitely many rectangles. So those rectangles become line segments, and when we add up infinitely many lengths of line segments, we get area. So infinitely many rectangles, summation notation, height times width, height times delta x, and now we know from the other page that the height is just that y coordinate. So the height is f of x sub k, and that f kind of little blurby there, but f of x sub k, and then we calculated delta x to be 2 over n. So now what we're going to do next is we need to figure out what that x sub k is. Because why I have to figure out that x sub k, and that's going to be my next thing, is the variable of the summation is k, and the variable of the limit is n. And so I really can't work with that x too well. My summation is in terms of k, my limit is in terms of n. Gonna be hard to figure out work with that x. So we gotta get rid of that x. So next, we need to find an expression for x sub k in terms of k and n because of what I just said. The variables involved in the summation and the limit are k and n. We'll know how to do the limit once the limit is in terms of n. And we will know how to do the summations once the summations are in terms of k. Gotta get rid of that x. We don't know what to do with the x in terms of the summation or in terms of the limit. So back to the picture, and then just coming up with going through a pattern so we can understand what we will be able to use. So let's just start with x sub 1. I'm going to cover some things up here. So starting with x sub 1. Let's look just at x sub 1. Go in a little bit. Okay, so x sub 1, that guy right there. It was my starting point plus the width of one rectangle. In this particular problem, the starting point happened to be 1, and that can change from problem to problem to problem. In this problem, it happened to be 1, then the width of one rectangle. The width of a rectangle was going to be delta x, and in this problem, delta x happened to be 2 over n. So there's x sub 1. Similarly, for x sub 2, right there, would be the starting point plus 2 rectangles. Starting point in this case was 1, and again, that can vary from problem to problem to problem, plus the width of 2 rectangles, so 1 plus 2 delta x, because delta x represents the width of a rectangle. So in this case, 1 plus 2 times 2 over n. And you could simplify that if you wanted. Doing it one more time, so we can see the pattern, x sub 3 would be the starting point plus 3 rectangles. That's how I get to x sub 3. 1, 2, 3. 3 rectangles. So 1 plus the width of 3 rectangles, 1 plus 3 delta x, because delta x always represents the width of a rectangle. So 1 plus 3, and in this case, 2 times 2 over n. That same pattern will continue. So x sub k will be the starting point plus the width of k rectangles. And so there is a commonality for all the problems. That your x sub k in general is going to be whatever your starting point is. 1, 2, 0, whatever your starting point is, plus k rectangles. So in this particular case, 1 plus k rectangles, 1 plus delta k x, or k delta x. So in this particular case, 1 plus k times 2 over n, or that's 1 plus 2k over n. But there's the commonality for all the problems, that when you have to find what x sub k is in terms of n and k, it's always this concept here. Starting point plus the width of k rectangles, or that would be start plus k delta x. That's always going to be how you can find x sub k in terms of k and n. That it's going to be whatever your starting point is, and that can vary from problem to problem to problem, and then k delta x, where delta x is the width of the rectangle. So there's what x sub k is. So going through it again. Again, I just kind of start over each time. I don't know why I started over each time. But again, what we were doing, we were finding the exact area. Our plan to find the exact area. was to add up the areas of infinitely many rectangles. Well, the way we're going to handle the infinity is the limit as n goes to infinity. We introduce summation notation, k equal 1 to n of each of the areas. Then the limit as n goes to 1 from k equal 1 to n, the way we get the height of a rectangle, or the area of a rectangle, height times width. The widths are going to be delta x. The heights we said were going to be f of x sub k. That f of x sub k, going back to this picture, gave me the height of that rectangle, that I just need to know that y coordinate there. The y coordinate there was f of x sub k. Okay, so that's where we got before, but now we know from the previous page, we'd calculated that x sub k is 1 plus 2k over n. So substitute in x sub k equals 1 plus 2k over n. And we also know, I didn't write that down there, that should be there. Recall, delta x is 2 over n, and so that goes right there. Do that one. There, that's better. So there's 2 over n. Then x sub k is 1 plus 2k over n, so I have f of 1 plus 2k over n times 2 over n. And now I'm going to apply my function 16 minus x squared. And everything else after this is really just going to be algebra. Now I have it all written down here step by step, but it is going to all be algebra after this. And again, if this blows your mind, this is just kind of foundational work that will allow us to do easier stuff later on. So you will live a perfectly happy engineering life if you don't master this. We want to understand the concept behind it, that we're adding up infinitely many rectangles, areas of rectangles, but you will do fine in life if you can't necessarily do all these calculations. So don't worry if this blows your mind. Okay, so we're up to here. All we did was we plugged in what we found x sub k to be, 1 over 2k, 1 plus 2k over n. Now I'm going to apply the function, 16 minus x squared. So this becomes 16 minus the quantity, 1 plus 2k over n, quantity squared, the whole thing times 2 over n. And now some algebra, step by step. Note the variable in the summation. So just looking at the summation, the variable in the summation, k equal 1 to n, it's k that is changing in the summation. So the variable in the summation is k. So the 2 over n is a constant as far as the summation is concerned. That 2 over n, just as far as the summation is concerned, is just a multiplied constant. It's no different than if it said 19 on the end. As far as the summation goes, that is just a number. It's a constant number. And so it can be factored out, but it still has to stay in the limit. So the first thing we did here is realize that that can be factored out, and all I did was factor out that 2 over n out of the summation, but now out of the limit. Okay, next, simplify by foiling and combining the like terms in the expression 16 minus 1 plus 2k over n quantity squared. So all I did here was FOIL that out. I very carefully FOILed it out. That's all that happened here. So all that's going on from here to here is FOILing. Which gives us all that. So all I did was FOIL at that. And then next, all I did was distribute that minus sign, and then 16 minus 1 is 15. So just some simplification. Now doing some summation work. Remember, you can split up summations by subtraction. So all I did there was split up all the summations by subtraction. On the next video, we'll continue with the algebra.